Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. And very good morning, everyone. So let's start the class with Umul Kitab Al-Fatihah and Doa. Bismillahirrahmanirrahim. Okay, so let me present the slide first. Okay, so the topic for today, okay, we will continue our lessons in week 9. Okay, you're already in week 9. Inshallah, there will be week 10 next week. Okay, so it's close to your final exam. Okay, so bear in mind, right? So this week we will learn about vibrations and wave. Okay, what the topic is about vibrations and wave. Some lesson plan will appear oscillations and wave. That is the same thing. Okay, so let you go. Now let's come to okay. So these are the learning outcomes of this topic. Okay, you can read by yourself about the learning outcomes. Okay, and it's until 16. Okay, we have until 1 until 16 learning outcomes. Okay, the combinations of learning outcomes from the topics of vibrations and also wave. Okay, so some heads up when you learn about this topic. Okay, you will learn about wave. That means some things that related to vibrations mode. Okay, so now let's look at the first figure. All right. So the first figure is about the force exerted by a spring on an object varies with the displacement like this one. Okay, let me have some laser pointer. Okay, so let's imagine a block that attached to a spring moving on a frictionless surface if the spring is stretched or compressed. So in this case of we want to learn about some things that related to spring and also that have been attached to some mass. Okay, but occasionally if the spring is attached or if the spring that attached to the mass is stretched or compressed. So what will happen to that? What will happen to that spring? Okay, so if the spring is stretched or compressed, a small distance x from its unstretched, or should we say as equilibrium position, and then you release it. Okay, what will happen? It exerts a force on the object. Okay, so as you can see, it exerts some force. That means some what we call that what. So in 1967, 1678, okay, Robert Hooke. Okay, the name Hooke's law came from this person. Well, the name is Robert Hooke. Performed an experiments using springs and found that the spring force obey the equation shown. This one, okay, F as equivalent to negative kx. Okay, where x is the displacement of an object from its equilibrium position. Remember, okay, x is the displacement of the object from its equilibrium position. That means the equilibrium position is at x equals to 0. Okay, right? So where x is the displacement of an object and k is the positive constant that we call that as spring constant. Okay, positive constant as spring constant. Okay, this is known as the Hooke's law. Okay, so first and foremost, this topic you will learn about a spring that is be connected to the mass and it contains some force that is given by Hooke's law, which is F equivalent to negative kx. And if you can notice that there is a negative sign in this equation, it means that the force that exerted by the spring is always directed opposite to the displacement of the object. It states that the negative sign at the Hooke's law stating that there is a restoring force. The word restoring force, that means when you want to pull the object to the right, okay, the object wants to go to the left, which means the object originally from right, okay, or originally from the equilibrium position, but you pull to the right end, so the object will tend to move to the original position. That means to the left. Okay, when you compress the spring, that means the object is going to the left end. Then the object will want to make sure that it move back to the original position. That means it wants to go to the right. So that's why we are saying that the force exerted is in the directed opposite to the displacement. But when you calculate the problems, you don't have to put the negative. So let's say here we have three different figures. Okay, a figure on the left, can figure in the middle figure, and also on the right end. Okay, so the spring force always acts towards the equilibrium position. It is sometimes called as the restoring force that I'm telling you just now. So let's say the block is initially pulled a distance to the right, okay, and released from rest, as shown in the figure. The force exerted by the spring pulls the block back towards the equilibrium position. So vice versa. Okay, all right. Let's see. Now the block, all right. Now the block is moving to the left or to the right. The spring force acts on it, okay, will be opposing will always oppose the direction. So the force increases the further the block gets from x equals to 0, and its speed decreases. Okay, as the force increases, the further the block gets from x equals to 0. Let's say from here. Okay, so the block will finally comes to rest at x equals to a. Is you can imagine here, when you pull one mass towards another situation, I mean another end, so that is what we call as some displacement over a certain equilibrium position. Let's say this is x equals to 0. So when you move this mass or this block towards the very right end, so that particular displacement is what we call as A. Okay, that means x equals to A. Okay, and then if you pull or if you compress the spring towards this end, okay, towards this end, so we are saying that the block E will be in the negative A, because the equilibrium position should be x equals to 0. So on the right end of the x equals to 0 will be the positive A with the positive value, and the negative side of the x equals to 0 will be the negative value. Okay, so the figure on the right then accelerate back toward x equals to 0. This process, as he rotates, okay, the process, remember, this is very important, okay, this process will repeat, okay, when you play with springs, okay, it always oscillates, okay, the process repeat itself, repeating again and again. So from this process, the block continues to oscillate back and forth. This type of motion is what we call as simple harmonic motion. So sometimes when you watch or when you want to find in the YouTube whatsoever, then go find the HHM simple harmonic motion. Okay, this topic is all about it. So what is simple harmonic motion? The simple harmonic motion occurs when the net force along the direction of motion obeys some Hooke's law. Okay, remember, obeys some Hooke's law, where the net force is proportional to the displacement from the equilibrium point, and is always directed toward the equilibrium point. Okay, so that is what I meant by simple harmonic motions. Okay, so let's look at this figure. This figure determining the spring constant, how to determine the spring constant, because the upward spring force balance the weight when the system is in equilibrium. It follows that K will be equals to mg with D. Okay, mg over D. Mg over D. Okay, that means based on F equals to Kx, you know that the X in here, it doesn't use X, it uses D. Okay, to substitute the X. Okay, think about an object suspended from a vertical spring. Its motion, okay, is a simple harmony. In this case, the force of gravity on the object stretches the spring until equilibrium is reached and the object is suspended at rest. Okay, when you don't put the mass, okay, at the spring itself, so we are saying that the spring is in equilibrium, or you don't have to pull, or you don't have to give some displacement to the block or to the object. So the spring, just make the spring and the block as it is. So we are saying that the spring is in equilibrium. That means x equals to 0. But when you compress or you stretch the spring with together with the object, that is what we call as x equals to a, or x equals to negative a. So by definition, the equilibrium position of the object is x equals to 0. So what I'm saying now, this is always remember the equilibrium position is where your x equals to 0. So when the object is moved away from the equilibrium by a distance x, and release a net force x towards the equilibrium position, because the net force is proportional to x, the motion is a simple harmonic motion. Okay. Here are three basic concepts which are important when we discuss any kind of periodic motions. Okay, the first one will be amplitude. Yeah, okay. The displacement we are saying now is x equals to a, or x equals to negative a, is what we call as amplitude. Okay, what is amplitude? Okay, the amplitude A is the maximum distance. Okay, the word is the maximum distance of the object from its equilibrium position. Remember, the maximum distance is not just an ordinary distance, but it's a maximum distance. From what? From the equilibrium positions. In the absence of friction, that means no friction, okay, an object is simple harmonic motion oscillates between position x equals to negative a and x equals to positive a. So try to imagine that. Okay, based on here, let's say if you go to this part, right? Based on this figure, let's say this is the equilibrium position, but in the have been put in the horizontal situation. Okay, let's say you compress or you pull the spring with the maximum distance. That maximum distance is given is called is what we call as amplitude. That means without any friction, if in the case of no friction at all, so the repeating motions of oscillations of the from the spring from the spring, so will make this it will make it so that we will define that motion as the simple harmonic motion. That is why motion comes from the repeating process of the spring and also the mass without any frictions. Okay, so number two is the T, the capital T. Okay, capital T is not a time. In fact, it's a period. So the period T is the, of course, is what is period T. Okay, we call it as T as a period, but the definitions of T is actually a time that it takes for the object to move or through one complete cycle of motion, one complete oscillation from x equals to x equals to negative a, and of course to go back to the x equals to a again. Okay, as you can see, maybe some of you have already did the experiments of simple harmonic motions in the lab session. So we are taking some, let's say, the position here and also the position here when the pendulum oscillates. Okay, it goes from this part, and then let's say the point A, and also it goes to point B. So what is one complete oscillation? When the pendulum moves from point A to point B and it goes back again to point A. So that is one complete oscillation that is given to you by one period. That means one T. Okay, one T. But how many times? Then you can still measure the time. Okay, then the other one will be the frequency F, right? With the small letter F. The frequency F is the number of number of complete cycles or vibrations per unit time. Remember, look at this equation. Okay, it is actually an inverse to the period. That means when you have a sum period, you can measure how many times that the complete oscillations occur in the consequence time, or in the per time. So when you want to find that, you can obtain the value of frequency. Okay, there are three terms that you can use here, which is amplitude, okay, the period, and also frequency. We can use Hooke's law and the Newton's second law to find the accelerations of an object moving in simple harmonic motions. For example, we have here, this is the F equals to ma, the Newton's second law, and of course the Hooke's law is F equals to negative kx. Okay, F equals to negative kx. Right? This equation is for the acceleration is an examples of harmonic oscillator equation. So what you call as harmonic oscillator equation, which give the acceleration as a function of position. Okay, acceleration as a function of position. How do I say that? Okay, so from F equals to ma, now you change this F, okay, and you know that this F is equivalent to negative kx, okay, negative kx, one. At the same time, F is also equivalent to mass times with acceleration. Therefore, we can rearrange this equation so that the acceleration is in the subject matter, and then we can have the terms of acceleration in the as a position, okay, in the what we call it as a function of position, as a function of position. That means a equivalent to the negative of k over mx. Okay, so remember, because the maximum value of x is defined as the amplitude, so the acceleration ranges over the values of negative ka over m to the positive ka over m. So remember, we can have both negative ka over m and also the positive ka over m. So in this case, we can say that the maximum value of x is given by just take the value without negative, which is the ka times m, because you know the x is the elongation, but in the repeating process of simple harmonic motion, okay, that means it's oscillating, that x is equivalent to the sum amplitude, we call as amplitude. Therefore, the acceleration will be k area. You derive this one, k, okay, we don't use this x because this is a normal elongation, and we change to some displacement, or we can call that as amplitude. Remember, amplitude is the maximum displacement. So these are some examples of the simple harmonic motion on a frictionless surface. Okay, so let's look at the problem. A 0.3, hold on. A 0.35 kilogram object, so this should be your mass, attached to a spring force constant. That means this is your K. Okay, your K is free to move on the frictionless. Remember, okay, the words come the frictionless, so we don't have to include the friction horizontal surface as in figure. Okay, figure 13.1, you can refer to your textbook. So if the object is released from rest at x equals to 0.1 meters, find the force on it and its acceleration at x equals to 0.1, x equals to 0.05, and x equals to 0 meter, and x equals to negative 0.05 meters. And the last one, x equals to negative 0.1 meters. So by using the Hooke's law, we can use F equals to negative kx. Okay, uh, then F max is negative k times a. Remember, the maximum is where the elongation is maximum. That means maximum distance. Then you can uh, hold on, you can change, or you can substitute the x into a. Remember, f equals to kx, but the x is maximum. The a amplitude is the maximum distance, so we can have a maximum distance over here. So in this case, we can have negative 13 new. Then look at the unit, there's still the same unit, Newton. Okay. So that is when we want to derive the force first, and then the first second one, you want to find the acceleration. This is just for the position of positive 0.1. Okay, a positive 0.1. That means the first one. Okay, but all calculations. Okay, we don't have to put all calculations here. It has been calculated. You can uh, when you are quite free, so you can try on your own how to get that force, and also there's some acceleration regarding a certain position. That means when x equals to 0.05 positive, x equals to 0, what will happen to the force and acceleration? Definitely will be 0 and 0 for the force, and then also acceleration, because F equals to ma, right? And what will happen when the x will be negative? Look at the value. All value is exactly and will be mirror to the how the force will be in the position where the position is positive. Okay, so you can try on your own on this part, right? So let's go to the next examples. Okay, a spring is hung vertically, an object of mass m attached to the lower end. Okay, and then is then slowly lower a distance d to the equilibrium point. Okay, that means spring is hung and an object of mass is attached. Let me attach first, and lower end is then slowly lowered to a distance d. That means some equilibrium position. Okay, find the value of spring constant if the spring is displaced by 2 centimeters. Displaced by 2 centimeters is where you have x equals to 2. Okay, x equals to 2, but 2 centimeters. Okay, we need to define that. F equals to kx, and all the amplitude and also x must be calculated in SI unit. That means you need to convert from centimeter to meter. And of course, the mass is in kilogram, okay, which is 0.55 kilogram. Okay, so how to do it? Now we may obtain. So this is where you have part A, part B, and part C. Okay, so find the value of spring constant if the spring is displaced by 2 centimeters and the mass is 0.55 kilogram. Okay, by doing that, okay, we may obtain some spring force and also some gravitational force. Remember, okay, when the position of object, that means here we may have some okay, we may have some force. Okay, how do I know this is a force? Because it's due to the spring. Okay, due to the spring, which means when we pull to a certain distance, which is at the amplitude, okay, this ball, of course, it contains some mass, and that mass will have its own gravity. Okay, so despite instead of the only gravity, the mass also have been attached to a spring where it also contains some spring force. So that's why when you look into the how they give some solution here, okay, it includes the gravitational force and also some spring force. So for the gravitational force is mg km times g, the negative sign where there it should be the negative because it's directed downward, and kd. Kd is the same spring force because the spring is F equals to negative kx. But in some calculation, we don't have to put the negative because the force is going to be upward. So we put that as a positive k, and d is the displacement of 2 centimeters. Okay, so when you want to find D, the answer will be some 2.7 10 power of 2 Newton per meter. Look at the unit used for K. Okay, because spring constant is contains is a base is a ratio between force and also elongation. Therefore, the unit is Newton per meter. Okay, so let's look at part B. If a second identical spring is attached to the object in the parallel with the first spring, that means you have put another spring that is attached parallelly with this first spring. Where is the new where is the new equilibrium point of the system? The new equilibrium point of the system. That means how can we know that this is the equilibrium point? Now you look back at the situation where you may find that in the equilibrium position, delta F will be equivalent to what we call the as 0. Okay, delta F equals to 0, or summation of F equals to 0. But remember now, okay, we may see that there is another spring that been attached to the first spring. That means parallelly. Okay, or we put it side by side. Okay, the second spring will be side by side. So right now we need to figure out what is the new equilibrium position. That means new D or new compressed that can make the situation become equilibrium position. Okay, so when you put another spring and of course the object, so now we may have some mg. Okay, and of course the F for spring 1 and also the F for spring 2. So it's given here negative mg kd2 plus another kd2. So from here we can obtain that d2 based on our terms will be half of k. K is 2.7 given from the first. Okay, from the first question, from the first part in questions, we can use that K to find the equilibrium position for the equilibrium point, which is at 0.01. Okay, 0.01 meters and about 1 centimeters. Okay, and the last one, what is the effective spring constant of the two springs acting as one? Okay, what is the effective spring constant? Because right now we put the spring side by side. Okay, side by side. So that means we managed to find what is the combinations of k when we combine it parallelly. So we can use this type of equation. Sorry. The summation of f equals to 0 that involves some mg and also spring. But this spring now be used as one system only. Okay, as one system. That means we can see that these springs only contain one system, just as the one we did in the first question here. Okay, we don't have to, because we have calculated at part B, we have calculated the equilibrium point for both spring that is parallel. Okay, so with the usage of spring constant, new spring constant, and then the answer of part B, which is the uh, equilibrium point for both parallel spring. So we can obtain the effective spring constant, which is at 5.4 10 power of 2 Newton per meter. So that is the value of effective spring constant. Okay, so let's go to the part where we will discuss about elastic potential energy. Okay, when you see this figure, it is about a ball projected from a spring. Okay, that means the spring where is inside the gun. Okay, inside the gun. The elastic potential energy stored in the spring that is transformed to into the kinetic energy of the ball. That means from the restoring force, now we want to calculate the potential of some energy happens when we release the spring inside the gun. As you know, the energy stored in the stretch or compressed spring or some other elastic material is called elastic potential energy. Okay, elastic potential energy. The figure shows a ball being projected from a spring-loaded toy gun. The spring is initially compressed, okay, a distance x. That means here, okay, it compressed to a distance x. So that means from the equilibrium position, it compressed to a certain x. When the gun is fired, the compressed spring does work on the ball and uh, imparts kinetic energy to it. That means it releases some kinetic energy from the elastic potential energy of the spring. Now it releases to the kinetic energy. Okay, as we know, the elastic potential energy for the spring will be half kx squared, where the k is the spring constant and x is the elongation or how the compression of the spring. Okay, so let's apply the law of conservation of energy. Okay, as of course, when we talk about energy, okay, we cannot put away some laws of conservation of energy, which is the energy initial equivalent to energy final. Okay, energy initial equals to energy final, and of course, we must include both gravitational and or spring potential energy. You can see here there's a KE, which is the kinetic energy. This is a PE for the gravity, and also for the PE potential energy of the spring and also PE for the gravity. Okay, if a non-conservative forces like friction are present, that with the case of let's say there is a friction inside the gun, then the change in the mechanical energy must equal the work done by the non-conservative forces. But keep in mind that we need to include rotational kinetic energy in both of these equation for system involving torque. If there is a torque involved, okay, bear in mind we have learned torque in the previous week, so we need to include the rotational kinetic energy. But right now, look into the cases one by one. Okay, take a look at the figure. Okay, this is the first figure, right? Now you have a block sliding on the frictionless horizontal surface collides with a light spring. Okay, in the absence of friction. Again, absence of friction. The mechanical energy in this process remains constant. Take a look at the figure. A block of mass M slides on a frictionless horizontal surface with constant velocity V. Okay, the total energy of the system is the kinetic energy of the block. Okay, again, the total energy of the system will be based on the kinetic energy. How do I know that? Because, okay, when the block slides towards the horizontal surface with some constant velocity, you know constant velocity is acceleration zero, the total energy of the system is the kinetic energy of the block. Okay. So for our discussion, let's assume the spring is very light. Okay, and I just spring. Okay, because sometimes the spring can be very heavy. But this one, okay, we assume that the spring is in light mode. And that means we can put away the mass of the spring. So we negligible the kinetic energy. As the block collides with the spring is compressed and it exerts a force to the left on the block. Now the block has a kinetic energy which is half mv squared, where v is less than v initial, v final is less than v initial, and the spring has a potential energy of the half kx squared. That means it comes with the kinetic energy half kx, half mv squared. Okay, and then when it uh, when it collide with the spring, okay, it will obtain some x. That means there is a elastic potential energy here. But when if the object is still moving, so that means it contains some v. So that's why it also contains some v final. But remember, v final is not equivalent to v before the collisions, because v before collision will get a higher value compared to v after collisions. So, when the block stops for an instant at the point of maximum compression, the kinetic energy is zero. Okay, as you know, the kinetic energy depend on the velocity. But if v equals to zero, so that means no half mv square. So we can assume that before it, with the total um, energy have been solely on the half mv squared collide with the spring, and if the spring is compressing at a certain time, so we can see that there is a elastic potential energy just as we discussed in the previous slide. Okay, it contains the half kx squared and it also contains half mv squared. Okay, because the box is still moving. Okay, but occasionally if the box stop at a certain after it reach some maximum compression of the spring, that means no v at all, then therefore all energy have been transformed into half kx squared. Okay, because the spring force is conservative and because there are no external force that can do work on the system, okay, the total mechanical energy of the system consisting the block and spring remains constant. Energy is transformed from kinetic energy of the block to the potential energy stored in the spring. Okay, as the spring expands, the block move in the opposite direction. Okay, again, after some times, okay, the spring expands and the block move in the opposite direction and regains all its initial kinetic energy as the block coming as before the collisions. Okay, so as you can see, as the block expands, okay, stretch back, the block will move in the other opposite directions and regain all its initial kinetic energy. So that is how you know the elastic potential energy comes from the total mechanical energy, which is involved mechanical, sorry, uh, some kinetic energy, okay, and it collide with the springs, and then all kinetic energy will be transformed into a potential elastic energy. Okay, elastic potential energy, and if the spring stretch back, okay, it release back all the energy into the certain kinetic energy because more the box is started to move. So as you can see in this figure, the elastic potential energy is stored in this drawn bow. Okay, when you play some archery, there is a bow and arrow. Here is a photo of an archer. Okay, when she pulls back on the bow strings, elastic potential energy is stored in both the bend bow and also the stretch bow string. Okay, when the archer releases the arrow, the potential energy stored in the system is transformed into the kinetic energy of the arrow. Okay, so from the elastic potential energy, it have been transformed all towards the uh, kinetic energy. So crossbow and the slingshot work the same way. Crossbow and also crossbow. That means, as we can see in the uh, very old school movie. Okay, how you fight back with the some bow, but this one is a cross one. Okay, like that one, and also a slingshot. Okay, slingshot macam plastic lah. Okay, let's look at this example about how can we know about elastic potential energy. A 13,000 Newton car starts at rest and rolls down a hill from a height of 10 meters. Slightly given that this situation involved in our daily life. Okay, so in that move across a level surface and collides with a slight spring-loaded guard rail here. Okay, this is your guard rail. Okay, this is the guard rail. So this car is moving that way, neglecting any losses due to friction. Again, okay, there is no friction involved in this type of question. Ignoring the rotational kinetic energy, that means it doesn't involve any torque. Okay, so find the maximum distance the spring compress. Assume a spring constant is K equals to 1.10 power of 6 Newton per meter. How to do that? Again, using some conservation of energies, loss of conservation of energy. So in here, we obtain only, okay, which means potential energy, gravitational potential energy, and which is equivalent to mgh. That is the only potential energy exists at the first stage. Okay, that means uphill, when the car is not moving yet, there is some height get from, because the car is moving downhill, so it contains some height. That height, okay, it will be used for us to calculate the potential energy of the car. And then afterwards, all potential energy have been, okay, transformed into some kinetic energy. But that kinetic energy now, okay, this car is collide with another spring. Okay, that means this is the potential energy of the from the gravitational potential energy, gravity. Okay, but here we have spring. Okay, in here we have spring. That means, okay, the kinetic energy, the outcome, it started from the potential energy, and it also uh, and with this some potential energy, but an elastic potential energy. So from mgh we have mgh, okay, mgh, and also it goes back to the half kx squared. Remember, half k x squared. This is the elastic potential energy. So all have been transformed there. And then we want to find what is x. Find the maximum distance. Okay, part B. So the answer is 0.51 meters. Okay, part B. Calculate the maximum acceleration of the car after contact with some spring, assuming no frictional losses. Okay, so that means calculate the maximum acceleration of the car after contact with spring. That means we want to find what will be the some acceleration when it can contact to the maximum spring or maximum compression of the spring. So we can use this equation, which is ma equals to negative kx, where a is the negative 380 meter per second square. Then lastly, if the spring is compressed by only 0.3 meters, find the change. Okay, find the change in the mechanical energy due to friction. That means if there is a friction, and the only friction involved in this question is in part C. Okay, so how to do that? then we want to find the difference between the initial and initial and after before collision and after collisions. So we can use the non-conservative work of ways to to find the problems. So from the half kx square, this all uh, minus with this one mgh. Okay, on the initial part, the initial we have mgh, and the final part we have half kx square. But this one, the spring is given to you 0.3, so we want to find what is the work, the mechanical energy due to friction. So when we can find some difference, okay, between the half kx square and mgh, so the difference is given by the friction, which is negative 8.5 10 power of 4 joules. Due to what? Due to some loss in the energy. Okay. All right. So I think I'll stop here. Inshallah, we will continue back tomorrow. Okay, with the topics, the same topics. Okay. So, so I think we'll continue tomorrow for the next slide. Inshallah. Okay. So thank you very much, everyone.